In this presentation, I will discuss how ShapeGenie measures the shape of the optic cup within the optic disc, specifically for glaucoma. I studied a data set called the ACRIMA dataset that was archived by Diaz-Pinto et al. In this paper. And here are examples of how I manually segmented the shape of the optic cup within the optic disc for normal cases and cases of glaucoma. Now, I like to point out that since I manually traced the optic cup, I had to only analyze images in which the edge of the optic cup was obvious, and I interpolated that optic cups typically have a round shape. Now, for those who will segment the optic cup using computational approaches, the edges of the shape will be much more jagged because the computer can pick out more detail than the human eye can. But that doesn't change the effectiveness of ShapeGenie. It just changes how the shape indices should be calculated from the resulting data, which I will talk about in a few minutes. Briefly, let me describe how the LCPC transform works, which is the core algorithm within ShapeGenie. So in step one, if this is the shape that you want to measure, since it's a closed shape, I apply the radial grid system, which looks for the center of the bounding box that would encapsulate the shape of interest. And that center is the origin from which radial grids emanate. And ShapeGenie will calculate the distance between every intersection of a radial line to this center point. And that distance is then linearized, as in step 4. Then we apply the fast Fourier transform to the data in step 4 to derive a frequency plot that represents the shape that we began with. And then, based on the frequency plot, we can calculate an index, such as summing all bins to get one number, or picking one particular bin to compare between samples. Now, there are two important methodological details that I need to point out in terms of how I analyze this optic cup data. First critical detail is that after I extracted the shape of the cup, I found the longest internal length, and I rotated every object such that the longest internal length was horizontal. By standardizing the orientations of all optic cups in this way, the data becomes much cleaner. We do this because nature inherently is polar. For example, North Pole versus South Pole, anterior versus posterior, so on and so forth. By standardizing the orientation like this, we discover that the data produced by ShapeGenie, it's much cleaner. The second critical detail is that I can only measure pure shape in these optic cups because the images that were archived were taken at different magnifications. And so there's no way of knowing the true scale of each object. So with ShapeGenie, it can do something very special that other technologies cannot. It can measure what we call pure shape. That is, for each object, I found the longest internal line, and I normalized all objects such that the longest internal line was the same length. In this case, it's 400 pixels long, but this is an arbitrary number. And the thing that when I resized, I made sure to constrain the aspect ratio so that I did not skew the image. And in this way, we can measure the effect of shape independently of the effect of area, which is impossible if you're measuring area, volume, and perimeter. But with ShapeGenie, it's actually very possible. So having applied these two methodological details, now let's look at the resulting data. So for the ACRIMA data set, we found that bin number 3 within frequency plots showed a clear difference between glaucoma patients and healthy controls. In order to confirm this finding, we did the same analysis on an independent data set, that is the data set from the Dristi GS study. And we found the same trend. That is, the bin 3 as an index of shape for glaucoma has a much larger magnitude than it does for healthy controls. Combining the two, this is what the data looks like. And I like to point out here that if you look at the scatter of the glaucoma patients, right, this is suggestive that we will be able to find substages using shape features such as the one that I measured in this presentation. Now, I'm not a glaucoma expert, nor am I an ophthalmologist, and so I cannot assess the labeling accuracy of the archived data. But as a computational biologist who studies image analysis and has examined hundreds of these glaucoma images, I'm confident that there are many features in addition to this one that will stratify normal versus glaucoma and stages of glaucoma for refined machine learning predictions based on morphology. For future studies, there are more features that should be measured in order to derive quantitative features for a machine learning model. One is to measure the cup and disc shapes at their original scale. We could not do that in this study because the archive data were taken at different magnifications, and so we can only measure pure shape. So it would be interesting to measure the shape of these cups at their original scale. However, this feature of measuring pure shape as we did is great news for the field because data imaged by different researchers at different places and different times will likely be taken at different scales. And thus, the ability to measure pure shape of an optic cup means that you can measure data taken by anybody, which allows you to have very large sample sizes despite difference in magnification. The second option, which I think is a very promising one, would be to measure simultaneously both the shape of the cup and the optic disc. Quite a few studies have pointed out that shape indices based on the distance between the edge of the optic cup and the optic disc were effective at quantitatively stratifying healthy versus glaucoma and stratifying different stages of glaucoma. Given this, measuring a shape index using ShapeGenie of both of these outlines simultaneously will give very powerful numbers to stratify glaucoma into its stages and likely help us find substages of glaucoma for earlier detection. And with this option, you can compare these shapes at the original scale and you can compare them as pure shape like we did in this presentation. Again, because the way ShapeGenie measures shape, it's quite different from traditional concepts such as area, volume, and perimeter.